All right. So welcome everyone to the first deep learning seminar of the year, like the physical year, not the academic year. Okay, so today we have the honor of having Paul Escande. So actually, I didn't practice. This is the best I can say your name, but I mean, I'm sure no one can say my name either, so it's fair. Yeah. So Paul is like a permanent researcher in Toulouse at the CNRS, and before he did his postdoc at Johns Hopkins University from 2016 to 2018, and before that, well, okay, we can keep going further, but maybe yeah, like
It's not too be long now. Not
I'm
that long.
terrible with introductions. So, but okay, but today I'm extremely interested to see this specific talk. So it's on the concentration of the minimizers of empirical risks. So this is recently published in JMLR, and after you.
Yeah. Okay, so thanks very much for invitation. And one more iteration because it's also not in time, but geographically. So I was a student in Kitchener, in the University of Waterloo back in the day. So I
Right.
don't know if it's an information that to share with you because no, I don't know if there are some competition between the universities. Oh, you've been disconnected from the host.
Really? No,
No, no.
no.
Yeah. So it's also a pleasure to present
Cool.
this work with you. And so yeah, it's about concentration of the minimizers of empirical risk. And as you said, it was published last year in journal. So if you want more details, you can check this paper with the same title. So presentation will be, we'll start with the problem, what's empirical minimization and why it's useful in machine learning, and we'll see how the work articulates with the literature, and then I'll present the main results and some applications. And so, I mean, maybe you all know about empirical minimization, but those slides are probably just to set the notations. And so will X of rho and mu. So rho is the distance, mu is the measure, a probability measure on the space. So it's a probabilistic metric space. And I also have another metric space that's called M, and I'm done with the distance theta here. And what we're doing in machine learning when we try to train a complex model, we can often be cast into the minimization of some function. Cost function or risk in statistics also explained. And usually it's so it's defined as a loss function that's integrated on the distribution of your data. And sometimes you can add a regularization because the problem can be posed and you want to impose some structure of the solution. And L, so L is the loss function that you are trying to integrate, and this defines the risk. So the risk will be called J, and it's the sum of F. So F is really, you can say it's a data term. So you try to, for example, make sure that your model predicts the right outputs of your model, and then you add the regularization. So R is the regularization. And I will call, so S will be the set of minimizer of J, and J star will be the increment of this risk. Okay, and so if you have questions, please interrupt me. I can try to answer your question. And so usually you don't have access to this full measure, your distribution of the data, so you can, oftentimes you have samples that are drawn from this distribution, and you have those samples xi. You have n samples of those distribution, and you, instead of trying to minimize the true risk, you do an approximation, an estimation of the risk with the empirical risk. And so f hat will be this empirical risk. So you sum all the risk on your data and you divide by n. And instead of minimizing the true risk J, you minimize the empirical risk J hat. And so S hat would be the set of minimizers of this empirical risk, and the minimum would be J hat and star. Okay. And so the fundamental matter question in the statistical learning theory is understand when the estimator of a minimizer of they had your empirical risk is a legit estimator. So, for example, um, what kind of guarantees can we keep on this estimator if you have so the minimizer of your empirical risk compared to the theorist? So this will allow to answer questions like how many samples I need to reach a given accuracy in high probability. So we'll be interested in proving some kind of bounds, like finding a function of delta and n. So delta will be the probability, we budget the probability the delta, and you can ask how many samples I need to have the distance between my two sets of empirical minimizers that are smaller than some value. Okay, and so you can work this inequality in many ways. We can also say, okay, I have this amount of samples. What's my probability for this error, or what is the error for this target probability? And here I'm not exactly using a distance between the sets. It's more like a similarity measure of those two sets. This distance is so it's, let's say, we're just one side of the observed distance between two sets. So it's 0 when S hat is included in the two sets of minima. It satisfies the triangular inequality, but it's not really distance, not symmetric. Okay, so maybe just some reminders to we are all on the same page. So I'll say so X will be a sub-Gaussian random variable. So we have a way to measure its magnitude. So it's the Gaussian sub-Gaussian norm X of when it's usually said. So it's an Ornitz norm C2, and we say it's a sub-Gaussian norm when it's tail. So sometimes people are more used to this notation, or sometimes this one, so I put both. But it's so when we say the variable random variable is sub-Gaussian, where its tail decays as a Gaussian random variable. So it's square over the magnitude, so the norm of the sub-Gaussian random variable. And we will also think about sub-exponential random variable. So it's the same. It's also defined by the decay of the tail, and it should decay as an exponential random variable. Okay. So you can check that those two formulation of the definition are equivalent. But what when we now we are interested in computing, so checking the accuracy of your empirical mean towards the true mean. We can use some concentration inequalities to prove that when we do an empirical mean of sub-Gaussian random variable, so the distance between the empirical mean and the true mean decays in this way. So it's a sub-Gaussian random variable. But this time, the random the norm of the random variable now is 1 over n, and the norm of the random variable x. And you see that the more points you have, the faster will be the decay. Yep. So that was the question, Mike. And now when you have a sub-exponential random variable, you see that you can still have the same kind of concentration bounds in a high probability. And you can prove that you have now, so this is a sub-gamma tail, but mainly you have the contribution of both the sub-Gaussian tails, sorry, and the sub-exponential one. So you pick the worst of the two words. So you have the subversion regime around 0, and then the tail at infinity behaves like a exponential random variable. So it decays. But you see that when you compute the mean of in an empirical way, the error decays as a square root of 1/n. And this is called what we say a parametric rate. It's when you try to estimate one value with the empirical with samples, the best rate you can get is 1/n, square root of 1/n. Yeah. So now I want to give 3 examples of how this abstract framework can be declined derived in 3 ways to see that it's quite general and what kind of function we are trying to minimize and what are will be the constraints and the properties of the function we will study. So there's a huge literature in the estimation in statistical theory, where they try to estimate to give rates on the estimation of barycenters of measures through samples, and so it's called barycenters or pressure means. And so in this case, so both the sets x and m are equal, and the loss function is the distance squared on the set, and you're trying to minimize. So the true risk is you try to minimize the true risk that's defined with the integral of the variance of the distance function, or the empirical counterpart is you minimize the empirical risk of this. So you compute the empirical variance and you try to minimize. And so in RD, minimizing those functions gives the expectation, the mean of the random variable, because that's the point that minimizes the variance of its variance function. And so with this in mind, you can compute the rates in quadratic risk. So the variance of your estimator to have the two minimizers is so the distance is also so this is the excess risk. So the value distance. So how far are you from the minimizer? And you can compute it exactly the variance of your random variable divided by n. And you can do the same thing with the concentration inequalities. You can prove that the distance between your empirical mean and the exact mean, so the mean of mu, decays in this fashion. So you still have this sub gamma tail for x being a sub-exponential, and still the rate is 1/n of the square root of 1/n. And so you see that estimating barycenter in RD is estimating d values, these scalars. So the rate is d times the parametric rate, because you are trying to estimate the coordinates of your vector. When you're not in RD, the situation is much more complex, because the risk is no longer so it's not guaranteed to have a convex risk. For example, in a non-negative, so in non-positive curved space, the risk is strongly convex, but in a positively curved space, the risk is concave, and it's much harder to get guarantees from that. So, for example, computing barycenters in Wasserstein space, which is a positive curve, is much more complex. And I have some slides at the end to explain how and why it's so difficult. And so we sometimes have non-convex function to minimize. Okay, so another example is a subspace estimation. So, for example, we try to find the leading direction of variation of your distribution. So it's finding the largest eigenvector. So the eigenvector that is associated to the largest eigenvalue of your covariance matrix. So in this case, so X, so your data is picked in RD. You're trying to find an eigenvector, so you're in the unit sphere of your in RD. And in this case, we don't have regularization. And so the covariance matrix for zero mean centered random variable is defined this way. So you're computing the covariance matrix of your data, of your distribution, and finding the eigenvector associated to the largest eigenvalue can be achieved this way. So you minimize the scalar product of covariance of to get phi the largest eigenvector. So this is the min-max theorem that is the characterization of the eigenvector. And the empirical counterpart is you minimize the same risk, but this time with 1/n sum of xi transport. And you can check that the loss function here is the scalar product between x, your data, and phi, the eigenvector. And you can also check that this function is not geodically convex on the sphere. One classical way to get a rate in this case is to use a matrix perturbation analysis. So in this case, it's the Davis-Stein theorem. So you can bound the distance between your true eigenvector and the empirical one by the distance between the two covariance matrices in spectral norm or Frobenius, up to you, divided by the eigengap of your covariance matrix. And you see that the closer are the eigen values, the harder it would be to estimate your eigenvector. And it's not surprising because you see you're trying to find the largest eigenvector for a ball. Okay, you pick mu is uniform, and it's an ellipse, but very close to a ball. Then if you don't, you're missing some samples in some area, you can mix what's the largest direction of variability of solution. And then to get concentration on the distance between the eigenvectors, can use some concentration of covariance matrices. For example, the what, because you can now concentrate the distance between the two covariance matrices. And so this example is quite nice also to see what's happening to do a numeric because it's very simple, and we can start to see how hard is it to describe what's really happening. And so here the example is we have a mu, so the distribution is a Gaussian with this covariance matrix. So you see that I'm not cheating because here the eigengap is very small, and so I'm plotting for many numbers of data. So I'm doing some Monte Carlo tests. I think I'm simulating maybe 10,000 different random realization of your the drawings of the distribution at many different numbers of points. And so in blue, I'm computing the quadratic risk of between the two eigenvectors. And you see that when you don't have many points, you don't improve the distance between the two eigenvectors. Does not improve, and it's quite like you have more and more samples, but it's not nothing happening. And then at some point, the error decays in a linear fashion. So you do observe the parametric rate of 1/n, but at some point. And you see that it will be related to a set. And this set, so I'm not telling you what it is now, but that's the theoretical set. It's not the one that so that's what we are explaining with the theory. And this set, you can see that there is this regime where the empirical risk, the minimizers of the empirical risk will start to be stable in some sense. I will explain it later. And in this regime, so when you see that the probability of not being in this regime goes to zero, we start to observe that the linear the parametric rate of the convergence of the risk. Okay, so obviously you can still use concentration inequalities of covariance matrices, but this will give you, let's say so usually constants are bad, but if you have good constants, then you can have a good fit of your risk. But with this bump here, you have to improve the constant. You increase the constant, and you are completely missing what's happening here. So it looks like there are also phase transition phenomenon between two regimes, where you are adding more points, but no, you're adding more points just to fall into some regime where you have the parametric rate. Okay. And so here you'll see later if you find that this set here is also it's it is described by the eigengap between the two eigenvectors of the covariance matrix, and when the eigengap is small, you spend more time trying empirically to be sure that your eigengap is sufficiently large, and then you fall into this regime of stability. Okay. So that's in this one. That's what we are trying to explain. What are the conditions that makes the empirical risk parametric rate, and also what is the behavior that for this to understand this phase transition between the two regimes. Okay, so another example is a regression. So you can cast the lasso in this abstract framework of empirical risk minimization. So this time, so we have 25 P. So is what are the coefficients that you want to apply to your features to fit your data and you do the regression. And this time you had the regularization, that is the L1 norm, and you can prove you can show that this is the true lasso if you know the full distribution, but the case and this is the empirical lasso, the counterpart of the and those two are convex problems, but we can observe different behaviors around the minimizers, because so when the covariance matrix of the data has a non-trivial kernel, a non-space, there are some direction when the data fidelity term does not change. And in those directions, that's where the regularization matters, because this term would be 0, let's say, and so you are just having a linear increase of the risk around the minimizer. But when you are not in the node space, so the data fidelity terms also write the risk, and in those directions, you will have a quadratic growth around the minimizers. So we will have different kind of behavior around the minimizers, and that will be very important in the kind of problems we are going to tackle. So those are examples are also to show and to see what kind of loss and risk we will encounter in the machine learning. So we have both convex and non-convex loss, and sometimes convex risk or non-convex risk. And we may have bounded loss or unbounded loss, and sometimes the domains are either bounded or unbounded, and unboundedness in concentration is much harder to tackle. And so the goal of this work was trying to understand this mechanism of concentration in the empirical root minimization in many problems. So what are the mechanisms, the abstract mechanism of the concentration in all those problems? So it was a hard question. Because sometimes when you have a, let's say you have a quadratic function, you can compute the minimizers, and sometimes it gives you a linear system to solve, and then you can do concentration inequalities, for example, with the matrix inputs. But as soon as you change your function, then you need to compute all the and really do many concentration techniques on your solution when you have the structure of the solution. That's not always the case. And so the idea here was to understand what's happening in a more abstract scale, and also in the end was to find user-friendly theorems that give optimal parametric rate, and to avoid this sketch of proof where you find the structure of your solution and then you do concentration, because each time you do the same thing. You have to compute the minimizer, you find its structure, and then you apply some concentration inequalities. But in the end, it's always the same mechanism happening. And hopefully, at some point, we'll be able to find these theorems that are user-friendly when you just have some quantities on your empirical risk, when you risk to compute, and plug in a theorem, and it gives you a parametric optimal at some point. And finally, the goal of this work was to describe this phase transition of the rate of convergence. So why is it flat at the beginning and parametric? Okay, so it's not no, it's a very old problem. It's no, it starts from 1974 with the work of Abut and Chavonakis. And so this seminal work, there is an extensive literature. There are many, like more than 10,000 papers studying those questions, but they are studying a different metric on the concentration of the concentration between your two estimators. So one is the excess risk. So it's the distance in function value between your minimizer, so the value at the minimum and the value at your empirical minimizer. And also we are now we are very interested in the generalization error. So what's how is my estimator behaving to data so that my minimizer haven't seen during the training? Okay, and so just to give you what's the typical bound, so usually it's proved when you have existence uniqueness of your minimizers and your loss is bounded, and the typical bound is looks like this. So you can concentrate in excess risk. In distance, the value distance between the minimizer and the value of your function at the empirical minimizer in this way. So you have two parts. One is the square root of n, 1/n, multiplied by c, and this is this constant c measures the complexity of the class of your function, and so it can be the Hadamard complexity, or it can be the covering numbers of your class, the entropy of your class. But I'm not going too much into those. And then you have this sub-Gaussian tail with this square root of 1/n. So you're showing that this risk decays at the square root of 1/n.
Just one question.
What? Yes.
Yeah. Why is the uniqueness required? Because you want, I think, like at least for generalization, like you only look at the integrated value.
Yeah. So it's just to simplify the proof, I guess.
Okay.
Then you can, yeah.
Okay. Yeah, I was like, okay, cool. All right. Cool.
Yeah, cool.
Good, merci.
And so there are two ways to get those down. So either you do stability techniques, where so that's a part of the literature that so the first work I guess was the yeah stability was Roger Wagner, and then there was the seminal paper of Bousquet in 2002. And there are many other kind of techniques for uniform convergence. So you try to bound this accessories by the supremum of some stochastic process, and then you need to estimate to upper bound the expectation of the supremum of your empirical stochastic process. And so there are many techniques from Talagrand on uniform convergence. And so there are kind of two different parts in the literature. And this bound, you can prove, so it's work of Levenson in 2008, that it is optimal if you don't assume other assumption on the loss or the risk. So that's the best you can do. But let's say now I'm trying to link this bound to proving a bound on the distance between the minimizers. And let's say you have a risk that is strongly convex. So you can prove that this inequality, so the distance squared times the strongly convexity constant of the function of the risk is smaller than the excess risk. So how far in the function value you are from your minimum, and then what you get is so my distance squared is smaller than so O of delta here is a shorthand for this this tail, uh, this one, so the sub gamma tail, and so you can show this. So you get this sub gamma tail to square root of 1/n with high probability, but if you apply this technique to the barycenter example, so on you get that the distance squared between so the two so the empirical mean and the mean is smaller than this tail, the square root of 1/n. Why? If you compute directly the with the concentration rate, or with this with the trick that with with these two so you see that it's decaying as 1/n. So there is a gap between what we obtain with this technique, so finding a bound a parametric rate on the risk, but we do not get the parametric rate on the distance. Okay, and this gap is known in the literature. So there was a question raised in a paper of Ferrell and Schwartz in 2009. So is then the estimation error, so it's the excess risk. So this excess risk here concentrate as 1/n for strongly convex function and Lipschitz cost. Okay. And we have to wait more than 10 years to prove that it was the case. We can achieve parametric rate on the 1/n on the risk. And then, so if you use this paper, you can prove that now my distance squared between the minimizer because I was 1/n. But so what the tools used in this paper, it's the behavior of the risk around the minimizers, and this will be very important in look at how my risk is behaving around the minimizer. Will have a crucial role in proving the optimal bound. But in this paper, we're still proving this one in the bounded case, and we start with strong convexity of the function. But at first, I was we were trying to explain the concentration of many problems that are really common. Okay, and then there are some other works that are from 2019, and here they are directly trying to prove the concentration rate on the distance, and they are also using this quadratic growth around the minimizers that mimics the behavior of the strong convex function, and they have some smoothness condition on L, and since they are using uniform convergence techniques, they need to rebound the entropy of the class of function they are minimizing on, and they can prove some parametric rate on the distance between the minimizer and the empirical minimizer. Um, in some cases, it does depend on the complexity of the space, and so for the barycenter example, we get optimal rate because in this case, E is equal to 1. So for Euclidean spaces and Euclidean spaces is equal to 1. So you can prove that you get the optimal rate that was shown before. But for more complex space, like that are non-positive curve, the rate can be cursed by the dimension. Because if the space is too complex, for example, D is equal to 2, then we don't get the parametric rate. But it's known from other works and other techniques that the non-positive curve space, the rate should be parametric already. So there is this gap with this work, and but it's very gives a lot of intuition and it's very nice work. And I will try to with this in mind show that in this case we can with the stability techniques we can prove the parametric rate without so that the rate does not depend on the complexity of the function we are managing. So what is this parametric regime? So the regime where the convergence of the risk is parametric. So I'll show some assumptions. There are 4 assumptions. They look a bit abstract and they are, but they're all generalization of some very common assumptions, and but they are allowed to go to the unbounded case. So the first one is a smoothness assumption on the loss. So it's very common when you want to show concentration to have a smoothness condition on the loss. Usually you assume some lead sheets or older smoothness of the loss. And here, so you can usually prove lead or the older condition on the loss when the domain is bounded. That's usually what we are able to prove. But when you try to tackle unbounded case, you need a much different, more fine, little finer assumption. So it's like we assume that so the loss, let's try this inequality. So you look at it closely. So you try. So this part is you don't change your data point. You don't change your data point. Sorry, but here you look at the distance when you change your function point, your t, and here it's the same. You pick a point y and you look at the differences between your left when you change p and c, and then you compute the 2 distances. And this should not be larger than a pseudometric. So here, pseudometric is a metric, but you don't have the implication when xy is equal to 0 implies x is equal to y. So it does satisfy the triangle inequality, but that's it. And should be smaller than the distance between p and c. So you can see that when L, so A is Lipschitz, A is L. Because so when L is Lipschitz, so this is smaller than L times the distance between P and T. this is the same, so we get to L times the distance between P and C. And so this can be seen as a generalization of a Lipschitz or Holder condition when you don't have a reference point in the metric space. Because here, for Lipschitz, you can think of, okay, now you want to have a Lipschitz function where the Lipschitz constant depends on the point you're at. Let's say you want to bound the distance between those two terms smaller than constant that depends on x and the distance between p and t. Okay, but since you're in metric space, what is the point I would like to have a reference on, and you can solve this question out by taking so the difference between so this is called the quadruple inequality because you take the distance between p and c and x and y, and you have this kind of down over here you have the metric of the space, and here also the metric between the points.
Can I ask a question? So
Yeah.
if your metric space is say locally compact, is this similar just to being locally Holder? Because you can maybe you can maximize this guy over balls if it's locally compact, you know?
Yeah, I haven't thought about it, but
I don't know. Okay, cool. I'll think about it. Cool.
yeah. Okay, so the second assumption was so I was saying that it's very important to observe what so the behavior of the risk around its minimizer will be important to prove this parametric rate. And so this is formalized in this assumption is okay in a level set of level J0, I'd like my empirical risk to grow faster than a predicted function around my minimizers. Okay. And this is mimicking, so when the function is strongly convex, you have this bound on the whole space. And so you can interpret it as, okay, let's say, so it's mimicking the growth of a strongly convex function around its minimizers, locally around the minimizers. Okay. So you can, okay, it looks like far-fetched, but many functions in the machine learning are satisfying this type of inequality. In fact, so it's this assumption has many names in different words. So in functional analysis, it's oftentimes called local Holder type around bound. In optimization, we often say it's a Loyasevic type inequality. And in statistics, it's also called the variance inequality, margin condition, and so on, and also benchmark. Okay, so many functions satisfy this inequality. So, for example, strongly convex function satisfies this inequality. Any semi-algebraic function on compact sets satisfies this inequality. And so this includes piecewise polynomials, square roots, functions, norms, many functions satisfy this inequality. But so they satisfy this inequality, but just you don't know the constant, and it's very important to know the constants. So there's an illustration. So what the smoothness and the growth conditions are. So you have this level set J0, and so you have the growth, quadratic growth around the minimizers. And so when the function is Lipschitz, so it tells you that your function has to, so the oscillation of the function has to decay as you approach the minimizers. And this is very important to have prove the parametric rate. And also, if your function is smooth, so let's say you're an RD and the function has a Lipschitz gradient. So you can prove that the function is stuck between two quadratic forms. And so you see that the oscillation are squeezed around the minimizers. Okay, so and this is those type of assumptions are you do avoid pathological oscillations around the minimizers. Okay, so this local error bound, so the quadratic growth, for example, you can prove that is equivalent to finding this constant now. Defined, so it's just the ratio here. So you divide this by the distance, and you have this tau, and you put the increment. And if it's positive, then you have you are satisfying this error bound. And so I'll make a third assumption is that when the level set is not infinity, so you have two different behaviors. When you are in the basin, so when your point is in this sub-level set of level J0, you have this local error bound, but outside you don't know what's happening. But so we'll impose just one condition on this behavior outside. Is not so you just impose that this behavior does not happen with high probability. So at some point, it's possible to be outside of this basin and we don't know what's happening. But the more points you add, you have probability you have to get into this basin where you have the local error bound. Okay. And that's something we can prove very easily in many cases. And so the fourth assumption, and that's the trick here, is that it describes the behavior of empirical risk around the minimizers. And this assumption, so we assume that I'm defining this empirical curve, this constant of your local error bound in this way. So it's the same as the true risk, but this time with the empirical function. And if this function tau is this constant tau is positive, then the function, the empirical risk, start to behave like the true risk. Okay, and for example, if tau hat is larger than 1/2 of tau, then you are now the empirical risk, so here, has to grow faster than the quadratic growth here divided by 2. So it grows, but a bit slower. Okay, so this assumption here is saying that with high probability, my empirical risk has to behave like my true risk. So it has to have this quadratic growth around the minimizers. So this is the hardest assumption to verify in practice, and that's what I will be working on in future works. But yeah, so that's the assumption. So at some point, when you add more points, and this is kind of intuitive because you can think of okay, I'm adding more points, so my risk, empirical risk, has to be converge to my true risk, and at some point, he has to share this local behavior around the minimizer. Okay, so I don't have much more time, but I'll say that, okay, so in this regime where so this set A, so the stability regime I was showing before, is this regime. So where you are in this, so your empirical minimizers fall into the basin of the local error bound, and when the empirical risk has the same geometry around its minimizers. Okay. And in this case, so this set A, we can prove that, okay, so the probability of not being A in case depending on the decay of this function, but usually you can prove that these functions are exponential minus n. And so it decays very fast. And when you are in this set, so the two points are in the set, you can, so now I have a set of points n, and I'm just changing one of them. Okay, so, and I'm defining two empirical risks, j hat with the x1 to xn, and j tilde with the x2 to xn, and y instead of x1. So I'm just perturbing my training set by 1 point, and I can prove that the minimizers of the two empirical risks is bounded by 1/n and some constant. Okay, and with that, so this is a stability of the empirical risk, because when I'm changing 1 point, I'm not changing too much the empirical risk. And if I have a lot of points, then I'm not changing at all. I mean, the more points you have, the smaller will be the perturbation on your empirical risk. Okay? And this will be very important to prove the convergence in the parametric rate on the estimation error, the distance between the set of minimizers. So when you are in this set, you can prove that so the quadratic risk, the quadratic distance in expectation between your empirical set and the true set decays as 1 over n plus some term that goes to 0. So that's the probability of not being in my stability set. Okay. So I'm speaking the proof sketch, and from that we can use some concentration inequalities, because now we know what's the mean of my risk. So I can now, with the stability, prove that my distance will concentrate around its mean, and the mean decays as a 1 over n. Okay. So, and then from that I can get a concentration rate. And still, so you have this, so you don't prove 1 minus delta probability. It's slightly smaller, because you have this probability of being in the complement of your stability. So I'm doing this also. And so what's very interesting with those results is, now if we check the assumption 1 by 1, then we have all the mechanisms that can, so you can apply this theorem and get the rates. And so on the barycenter problem, you can prove that all the risks are strongly convex. So the empirical risk and the risk are convex with constant 1. We do satisfy this quadruple inequality, so the smoothness of the distance. And so then you have stability of the minimizers, the empirical minimizers on the whole set, on the whole space. And you can prove this parametric rate with the stability techniques, and it's not depending on the complexity of them. So we get optimal rates as like those two papers. Same thing, we can prove that, so with this set A, we can show, we can predict what's the bound here I was showing before in the production. The bound in the green here is the bound that's given by our theorem. So you can see that we can fit a lot more what's happening. So the phase transition between the two regimes, and then we get the stability rate. And finally, so for Wasserstein, it's much harder, because we can't prove this quadratic work for any measure in the space. So it's very measure dependent, and there is this nice paper that describes what kind of bound we can expect for well-behaved measures in complex. And we can apply this framework to showing some Wasserstein barycenters that are regularized by the entropy, that we can also have this parametric rate. So just to say a few words on the future work. So we saw that, so we have this abstract assumption. Some are very simple to check by hand. It's very simple, like proving that with high probability you fall into this sublevel set. It's really very simple. But proving that your function, the geometry of your function, empirical function, start to behave like your true risk around its minimizers is much harder. And yeah, for me, it's the most open problem now, and that's what I'm trying to work in. Thank you for your attention. I'm really glad to take questions, and hopefully I'll see you in person sometime.
Let me, okay, there's the clapping emoji. Oh, thank you. Thank you very much. I'll quickly ask if there are any questions from the audience before. Okay. Oh, maybe people are shy or hungry. Oh, no, okay, cool. To be honest, like my main question was going to be related back to non-positive curvature, but
Yeah.
then you did it, so I was like, I have no more questions. Um, okay, but maybe I just like a cheap question like follow up. Um, yeah, so I know there's some results that say that the like okay, if you're in a Riemannian manifold with yeah, like positive
Yeah.
like scalar curvature, then like in a small ball, your metric is also convex. Um, I think yeah, there are some very niche results on this. So globally, no, like you said, but apparently locally, yes, but very locally.
Yes.
But
So I
depending,
think
like
in the Wasserstein case, the tricky part is that depending on what type of measures are in the ball, so it can be infinitely curved. So
mm,
the ball has to have a radius very small, and at some
yeah,
point, so, and
yeah, it's like
then you
one.
don't get yeah,
Yeah, okay, yeah, that's what I was gonna ask. Yeah, because it's like one over c or root c or something like this, and that would. C is
yeah, yeah,
the curvature. Okay. Okay, so then okay, cool. Okay.
yeah. So yeah, so they have um, a way to describe what kind of measure you are computing the barycenter can be you know, where you can prove that they have this product work. And many, so I think so the thing is that you should be able to find the convex, strongly convex and smooth potential just
Okay, yeah.
from the transport lab. Yeah. But,
I see, I see. Okay. Okay, so that was the main problem. Cool, actually. Okay, those are my two questions, but mainly the first one you already answered. Um, so I'd say thank you very much again to Paul,
thank
for
you.
being our first speaker of the year.
It
And
was my pleasure. See
yes, and yeah, see you around.
you around. Thank you very much.